So I've written down two additional theorems. This is very short. It's easy to prove that. So I've added another one here. So we'll prove this, and then we'll come to this one and prove this one. So this theorem says that if G here is a group, then for any x in G, we have that x inverse. The inverse of that is equal to x. The inverse of the inverse will give you back the element x. Okay, so basically that's what it says. So let's prove that. Okay, it's easy. Now if let's start from here. Proof. This is for theorem 1.3. Okay, so if G, so you let G be a group, let G be a group, all right, and X be an element in G. Well, since G is a group, X definitely has an inverse, and if it has an inverse, then of course X star X inverse star X must be equal to the identity element in E. You can define it up there too, right? Where E is the identity element. So this holds if G is a group and X is an element in G. Okay. Now we want to show that the inverse of the inverse is equal to X. Okay. Now the easiest thing is, well, note first of all that, okay, so note if A is the inverse of X, and I write AX is equal to X A, and I get this back. What it means that one is the inverse of the other, right? I can write A as that, or X is A inverse. When this holds, one is the inverse of the other. So once these three, maybe two equations, once this statement here holds, I can always do this. Okay? Then A is the inverse of X, or if you like X, the inverse of A. Okay, so that is the idea. So basically using the definition of what the inverse is in the group. Okay? So we have this. And so basically I could actually do that here, right? If this is it, I can say that X is equal to this inverse. And I'll just, and that's the proof. Or this is equal to that. Well, you can also say let Y be equal to X inverse. Then what that means is that here I'll have X star Y, right, is equal to Y star X is equal to this. Okay, Y is in G, but if this holds, then one is the inverse of the other, right? So this basically means that X is equal to Y inverse. If I say Y equals X inverse, all right, we have that already, so we don't need that. So X is equal to Y inverse, but we know what Y does. Y is equal to this. So wherever I see Y, I can replace with X inverse. So this is equal to X inverse, all inverse of that. Therefore, right? Therefore, X is equal to X inverse. Okay? So that is what we wanted to prove. So that is straightforward, right? It's kind of short, basically from the definition of what the inverse of an element is in a group. Good. The next one is theorem 1.4. This says that if G is a group, right, and X and Y are elements in G, then X star Y, the inverse of this guy here, is equal to Y inverse star X inverse. The order is very important. Okay, so pay attention to the order. If X was, if G is an abelian group, right, which means it's commutative, then the order is not important, right? Y inverse star X inverse will be equal to X inverse star. But in general, all right, we are not told it's abelian. In general, this is how it should be, right? X star Y inverse should be equal to Y inverse star X inverse. So how do you prove that? Well, we can use this idea of inverses, right? This basically means if we can show, right? So let me get rid of this, right? So we have proof. So we now want to prove 1.4. Okay. So let's prove 1.4 now. So we have I mean, we are doing these proofs because we'll need them later on, right? In some of the other concepts that we are going to learn, once we have these proofs, it will be easier to understand and prove some of the theorems in those concepts as well. So that is why we are doing these. We'll apply them later on. Okay, good. So you see, this inverse means that this quantity here, x. So I haven't started proving yet. I just want to explain certain things before we do the proof proper, right? I take this. Well, the inverse of this will be this quantity inverse, right? So if I can show that this times, if you like, times its inverse. Now the inverse of all of this guy will be this, right? If I can show that this times this, okay, if you like, and also show that inverse star y is equal to what? If this is actually this, if this is the inverse of this, right? Then this star this and this star this should give me the identity from the definition of what the inverse is. Okay. So we'll just take one side of it, right? Let's just take this side of it. This side. So this means if I'm able to show this x star y inverse, right? If this is the inverse, then this really holds. Okay? Now this theorem says that this guy here is actually this. Okay? Which means that if I can plug this guy in here and show that if I operate this on this, I get E, then of course this guy will be equal to that quantity. Okay? So that is the basic idea, right? This, and this should be E. So let's take one side. This and this is E, but the theorem says this guy here is this. Which means if I can replace this, if I can put minus y minus x here, start it with this guy, and the result is E, then of course this is equal to that. Okay, so that is the idea of the proof. Okay, so I'll leave, cancel, this is not it. So to prove it, we say of course let G star be a group, right? And let x and y be elements in G. Okay. So how we're going to do basically this idea here. We're going to take x star y. Okay. I'm going to start this with this guy. Y inverse x inverse. I'm going to do this and see what I get. Okay. This is equal to, well, star is associative, so I can regroup these guys. I can write this as x star y inverse star x inverse. Okay? This guy here is the identity, right? So this is x star e star x inverse. Well, if I can group this or that, it doesn't really matter. This and this will give me x star x inverse. X and x inverse gives me what? E. So this star this gives me E. You could do the other way around, right? You can also show, you can try it. Also show that if I reverse it, if I do y inverse star x inverse, if I do this against x star y, I get E. Okay, see, 1 and 2, that's where I'm deriving that. So you can also show that this is E. If that is the case, then this guy here is the inverse of this, right? So hence, okay, hence x star y, the inverse of it is equal to that quantity, this quantity, right? Y inverse star x inverse. You see that? So you start with this. So we assume that it's an inverse if both this poles, both of them, all three, this and this must be present for you to see that one of them is the inverse of the other. Okay, that's why you need to do this side as well. Oh, what is it? Yeah, this. Okay. So that is straightforward for this one. So we'll have a couple more. Okay. So I'll stop and I'll write a couple of more theorems, maybe two more theorems on cancellation laws. Okay, and then we go from there. So try your hands on these ones. There's always different ways you can do these proofs. Okay, so try your hands on them.